Welcome. In this mini lecture, we'll go over the key definitions in sections 1.4 through 1.6. Let's begin with section 1.4. Here, our key definition is that of a power set. If A is a set, the power set of A, denoted by a script P of A, is defined to be the set of all subsets of A. And in fact, if A is a finite set, then we know that the size of the power set of A will be equal to 2 to whatever size of our set A is. So let's look at an example. If we have the set A being 2, 3, 5, 7, we want to find the power set. To do this, we're going to list all the subsets of A. We can start by taking the empty set, which if you remember we discussed was always a subset of any set. Then we can take the elements one at a time. Now we can take them two at a time, so 2 and 3 together, 2 and 5 together, 2 and 7 together, 3 and 5, 3 and 7, 5 and 7. Proceeding now with subsets that have 3 elements, we can have 2, 3, and 5. We can have 2, 3, and 7. We can have 3, 5, and 7. Now we can also take the whole set itself, 2, 3, 5, 7. This should be the power set of A. If we've done everything correctly, we know that our set should have 2 to the 4th or 16 elements. Let's go through and check and see if we've got 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oops, we've missed one. Which one have we missed? Maybe pause the video here and see if you can find it. Hopefully you found a missing 3-element set. Which one was it? 2, 5, 7 was the missing set. In section 1.5, we define the union, intersection, and difference of two sets. The union of two sets is the set of all elements that are in A or B. It could be in both, but as long as it's in one, the element will be in the union of A and B. The intersection of two sets is all elements that are in both, so it must be in A and it must be in B at the same time. Lastly, the difference of A and B is the set of all elements where X is in A and X is not in B. So let's consider two sets. Perhaps A is the set 2, 3, 8, 12, 17, and perhaps B is the set 1, 5, 8, 17. In this case, A union B would be the set of everything that is in A or B. As long as it's in one of the sets, it's in the union. So we would have 1, 2, 3, 5, 8, 12, and 17 in the union. In the intersection, we're looking for all the elements that are in common to both sets. Examining the sets, we notice that 2 is not in both sets, 3 is not in both sets. 1 is not in both sets. As we continue down, we find that the only elements A and B have in common are 8 and 17. Now, examining the difference, we're going to look at every element and determine if it's in A and not in B. So, 2 is in A, and it is not in B. So 2 is in our set. 3 is the same. 8, when we look at 8 is in A, and 8 is in B. So we are going to leave 8 out of the difference. 12 is in A, but not in B. 17 is in A, but 17 is also in B. So we will leave 17 out. Now in this case, we notice that, say, 5 is in B, but not in A. Even though it's in one of the two sets, because it's not in A, it's still not in the difference of A and B. Lastly, in section 1.6, we look at the complement of a set. So, if A is a set with a universal set U, the complement of A, denoted by A bar, is the set of elements that are in the universal set, taking away the difference with set A. So perhaps we have a universal set that contains the elements 1, 3, 5, 7, 9, 13, 17, and 23. And perhaps the set A is 1, 5, 17, and 23. In this case, the complement of A is everything that's in U but not in A. Again, looking at the difference of the sets. So the complement of A, 3, 7, 9, 13, and that would be the complement of A. If you notice, A and A complement together is equal to the universal set. That's all for now. Thanks for listening.